The other main structuring feature in MaxScript is the function definition. We've met several functions before, like copy and rotate and distance and so on, but these are all built into MaxScript and form a fixed library of tools. You can also create your own functions and build your own function libraries. To beat our poor sphere creator example into the ground, let's make it a function. This says, define a new function named createSpheres that takes two parameters, count and growth, and does this when you call it. This is called the body of the function, and it can be any expression or statement, or of course block. Then anytime you wanted to create a sphere collection somewhere in your code, you'd call the function rather than typing in the whole for loop again, like this for example. It is very common to wrap a piece of script in a function definition like this if you find yourself needing to use it in several places in your code. By factoring it out into a single definition, you get to write a simple function call in each place it's used and only have to keep up to date one copy of the shared code. Note that I've made our function somewhat general by having it take two parameters, so it's more useful than if it took none and always created, say, 10 spheres with a growth of 5. When you define a function, you can have it take as many or as few parameters as you want, so you can generalize its use as needed. Let's take a closer look at the parameter mechanism. In the definition, you see I define the parameters required on a call by including a list of names, one for each parameter. Then, in the body of the function, I refer to the parameters by name, here for the count and here for the radius growth. Each different call of the function will cause the body to run and bind the actual call parameters to the parameter names in the body for that call. Let's look at another example that uses optional keyword parameters. Suppose in this case I have a pretty large script that is building a complex scene, perhaps under the direction of some data in a file or spreadsheet. And at various points in the construction I want to generate some test renderings from a bunch of cameras scattered around the scene. Here's a function called snapcams that will do this. When you call this function, it will loop over the cameras in the scene and render a snapshot image or video for each camera out to a series of files. You call it with a labeled text string that identifies the particular snapshot and that is used to create the output file name, and optionally a frame size, frame range, and destination folder. Here's an example call. The string phase1 is the label parameter, and I've supplied just one of the optional parameters. You can see the parameter definition section here is quite a bit more complicated. It defines one required positional parameter, label, and three keyword parameters, size, frames, and folder. The keyword parameters, if any, must come after the required positional parameters and are signified by having the colon after the parameter name. For two of these, I included default values after the colons if either is not supplied in a particular call. The frames keyword parameter is optional and I didn't give it a default. This lets me check inside the function to see if it has been supplied or not and to choose either a JPEG single image or AVI movie as the output format. Keyword parameters are used in the body the same way as positional parameters and also act just like local variables. Let's quickly walk through the code. The outer for loops the variable C over the cameras in the scene. Cameras is one of the built-in object sets. Then, I construct the first part of the output file name by concatenating the destination folder, supplied label, and camera name. I will add the type suffix when the code figures if it should be an image or a movie. The plus operator works on text strings as well as numbers, but for text it simply concatenates them into one larger string. If the frames parameter is not supplied on the call, it'll contain the special value unsupplied, which I can test for in this way. In the unsupplied case, I assume you want a single frame snap and call the built-in render function. This function is extremely powerful and lets you access most of the capabilities of the Max rendering system, having upwards of 50 keyword parameters. I specify the camera to render, the output frame size, and the output file name. Since this is a single frame snap, I add the .jpeg suffix to the file name to tell the render function to generate a JPEG image out. If the frames colon parameter is supplied, I'm expecting it to be a frame interval, include it as a parameter to the else branch render call, as well as setting a .avi file name suffix so I get an AVI movie file as output. You also notice this call to the render function is split over 2 lines. In order to tell MaxScript that you're continuing the function call, as opposed to writing 2 separate statements, you stick a / continuation character at the end of the line. You can continue any statement across any number of lines like this, if needed. Okay, another example. As with the built-in distance and copy functions, scripted functions can also return values. Let's say I was writing a script to build a number of objects, and I wound up creating a similar material based on the cellular texture in several places in the script to assign to different objects. Rather than recode this every time, I could define a function once, like this, and call it in each of the places I needed to create a new version of the material, like this, for example. The function has 2 parameters for setting base color and cell size, and simply constructs a standard material with specific parameters and a cellular texture with parameters based on the function parameters, and then assigns this texture as the diffuse map for the created material. The final statement here sets the return value of the function, in this case the material we just created and textured. Let's do one final function example showing how functions can be used recursively to easily work on nested structures like the scene hierarchy. Let's say I have a scene containing deep object hierarchies, and I want to apply versions of the previous cell material to all the objects in a hierarchy such that the material parameters vary depending upon nesting depth. For example, here's a scene showing a hierarchy of boxes, and I want the material at each level to shift in hue and down in cell size. One simple way to do this is to write a function that will take the cell material parameters for a given level, apply the appropriate material for that level, and then compute the parameters for the next level and call itself again on the child objects to apply those parameters to the next level. Here's a function called material_to_children that will do this. Let's run it first. I call the function giving it box01 and a starting cell color of blue and cell size of 10. Alright, let's see what it has done. Yep, the hue starts out blue and shifts toward red, and the cell size is decreasing down the hierarchy. The function takes 3 parameters, an object to apply the cell material to, and the parameters for the cell material at that object's level. The first thing it does is call the cell material generator with the given cell parameters to make a material and apply it to the object we are given. Then it runs a for loop over the object's children, calling itself again on each child, but with adjusted material parameters, adding a bit of red into the current color and bumping down the cell size. This will re-enter the function for each child and will set each child's material according to those modified parameters. Then look to see if any of the children themselves have children, calling the function itself yet again on those children with further adjusted cell parameters, and so on, setting up a kind of loop that runs down through the entire hierarchy underneath the original top-level object. At each level, the function computes new cell parameters for the next level, based on the current level's parameters. So, if the cell size starts at 10, for example, the first level down will be 7, then the next will be 4, and so on. Here I'm doing some color arithmetic, adding an RGB vector containing 75 red, 0 green, and 0 blue to the current level's color, bumping it further towards red as it loops down through the levels. This technique of having a function call itself is known as recursion and can be extremely powerful.